Okay, thank you. Dear ADS3701 students, welcome to yet another presentation. Again, my name is Dr. E Mazibe, and I'm the lecturer for the module. So this presentation is based on the second unit. More information will be found in tutorial letter 501. But this presentation is just to help clarify some of the concepts that may be complicated for you to understand if you're just reading by yourself. So you'll notice that in the unit, we're basically discussing what's out there, what is beyond the solar system. In the previous presentation, the focus was on the solar system itself. So we will be discussing firstly the universe, which basically refers to everything that is found in space and time. That includes you, that includes the air that you breathe, that includes the device that you're using now. So the universe is so big that it contains organized structures on different scales. For example, within the universe, you find galaxies, and within galaxies, you'd find solar systems, and then you would find stars, and then the stars would obviously have the planets creating solar systems, and then the planets will have bodies that orbit them, which we call moons, and then you'd find material that did not accumulate into planets, but it still orbits, the material still orbits the sun, and we call that asteroids. Now in space, we also find that there is radiation, for example, light and heat. There are also magnetic fields and also high energy particles, for example, cosmic rays. And then we move on to discussing stars. So, for example, our very own star, our very own sun, rather, is actually a star. So a star is basically a glowing ball of gas, for example, our sun, like I've indicated, but it starts off as a gas cloud. If you remember in the previous discussion, I talked about the nebula theory, which described the formation of the solar system. So the sun also forms from a nebula or a gas cloud, which is initially spread out. Now, gravity, of course, is a very important force in the universe. So it collapses the cloud. So it brings the cloud together. So the collapsing of the stars basically causes it to heat up. And if the temperature can reach 10 million kelvins, then it can ignite a fusion of hydrogen into helium. And that's what gives the birth of the star. So that's how a star is basically born. Now, if you look in the night sky, obviously you would see different stars, and you can start picking up some patterns or shapes of the organizations of stars. If you can look a couple of stars that are closer together, you can imagine a shape that these stars basically form. So this is how stars were actually grouped by astronomers, the groups are known as constellations. And the groupings have and their significance varies across cultures. Of course, some people treat the stars as gods, or they use the stars to celebrate heroes across their cultures. But the stars were also served as guides for harvesting and navigation, becoming, of course, the first calendars. So what you need to understand is that if you look at the night sky in different times of the year, the sky wouldn't appear the same. Because remember, you are orbiting the sun. You are on planet Earth. The planet Earth is spinning about its own axis, giving you day and night. But 6 months later into the year, you find that you are now on the other side of the sun. So now when you look into the night sky, the stars that you see are different from the stars that you saw 6 months ago, because you are now in a different location from where you were 6 months ago. So the groups of stars that you see across time within a year can help you find out what time of the year is it? Is it time to harvest? And you can also use them. They were also used for navigation. Now, this is a very important concept. The distances of stars, how are they determined, or how are they determined by astronomers? Now, what you need to understand firstly is the fact that stars are very far. like extremely far, that we don't measure them in normal distances that we use to measure maybe how far your house is from your friend's house, how far a certain city or certain country is, or yeah, we don't use like your kilometers and meters, centimeters. Those are for smaller distances that actually these distances are comprehensible by our brains quite easily. But when you talk about the universe as a whole, you talk about galaxies, the edge of the universe, then it becomes difficult for our brains to sort of comprehend it because it's very far. So we measure distance in light years. Okay, so in the previous discussion, in the previous presentation, we had a thorough discussion of a light year, but basically this is the distance covered by light in a year. Okay, now understand that light travels at a velocity of 3 times 10 to the power 8 meters in a second. And you can imagine how much distance does light cover in a year. That tells you how far a star is if it is 1 light year away from you. Okay, now astronomers use parallax to measure distances of stars, as shown in the diagram here. So parallax is basically the apparent shift of an object. For example, if you can close your eye, one eye, and open it later, close it and open, close and open, and look at one object, you would see that the object appears to shift left and right as you close and open your one eye, while the other eye is open all the time. Another example of parallax is to observe objects. When you're inside a car, you're driving, you're inside a car, you observe objects that are closer to you and objects that are further away from you. Now, you've noticed that the objects that are closer to you, like trees, you'd see that, or traffic lights, things that are closer to you will appear to move. But things that are far away from you, like the sun, doesn't appear to move, which means the distance helps us in determining the parallax that we need in order to obtain the distances of stars. So now how do we do that? So you'd be positioned here sometime in January, and then you see a star. So you can see this dotted line here basically shows the path of the light that will be traveling from the star to your eye so that you can be able to see it. So it appears as if the star is somewhere here. Now, 6 months later, we are now in July. 6 months later, you are now on the opposite side of the sun. Okay, you are now here in July. Now, when you look at the very same star, it appears as if the star has moved that way. So it has moved upwards as shown on the slide here. Now, if you can measure the angle here, so using the sun as the reference, and then you get the angle theta, then you can use that to determine the distance of a star using a method known as parallax. Okay. Now, of course, parallax has its own limits because, like I've said with the example of a car, objects that are very far do not appear to shift when you are moving. So you are in one location, you look at the sun, and then maybe a few minutes later, you are somewhere else and you look at the sun appears to be in the same place. And the same thing happens with stars that are quite far, like very, very far, more than 400 light years away. Okay. Now, in this case, of course, parallax doesn't work because the stars don't appear to shift sideways. So if you turn around, so one moment you are, or in June, you are in a certain location around the sun, and then after 6 months, you're in another location and you look at the very same star, the star appears to be in the same place because it's very far away from you. Now, astronomers in this case then use color to determine distances of stars. So now you need to remember the spectrum of visible light, which ranges from red to violet. You know the Roy G. Biv spectrum: red, orange, yellow, green, blue, indigo, and your violet. You know that's full spectrum of light. So the red corresponds with low frequency, with low frequency but long wavelength radiation, and then blue and violet corresponds with high frequency but shorter wavelength. So now if you see a red star, then you'd imagine that the star must be cooler than a blue one, and it will therefore be fainter. But if it happens that you see a star and the star is red and the star is significantly bright, then you know the star has to be much closer to you, okay? And then astronomers also use what we call luminosity in order to understand stars. And that is a measure of total energy emitted by a star. And the importance of luminosity is because if you look at apparent brightness of a star, you may think that maybe a star is producing a lot of energy, and you find that the star is not really producing a lot of energy. It's just that the star appears to be bright, and it could appear to be bright because it is much closer to you. Therefore, luminosity is what astronomers use in order to sort of get like a more accurate description of a star in terms of the amount of energy that it emits. And the Russell-Hertzsprung diagram is basically a diagram that is used to sort of map out the relationship between luminosity against temperature. As I mentioned earlier, that if you look at apparent brightness, then you're not getting a true reflection of a star. So you see a star is bright, but if you conclude by looking at brightness only, then you may not be accurate enough. So you need to go beyond just talking about apparent brightness. So you look at luminosity, and then through luminosity, you can sort of try and work out the temperatures of stars. Now, luminosity is, of course, expressed using the letter L, and it's expressed in relation to the luminosity of the sun, L sun. So this symbol here, L sun, basically represents the luminosity of the sun, and then the luminosity of other stars will be in relation to that of the sun. For example, Betelgeuse is 38,000 times luminous times the luminosity of the sun. Okay, that's why we express it as 38,000 L sun. Okay, now if you look at the diagram, which is in the next slide, luminous stars are placed at the top, right? Dim stars are placed at the bottom. Okay, and then you have the hot bluish stars that are towards the left, while the red cool stars are towards the right. We know blue is associated with hot, and then red is associated with cool. And then we have stars that are in the main sequence. For example, our sun. Our sun is a main sequence star because it fuses hydrogen into helium. For your own interest, the star that we have, our sun, was born about 4.5 billion years ago, but it still has about the same amount of time to live before it starts dying and moving out of the main sequence, but we'll discuss later in the presentation. Now, the lower left of the diagram has dim stars that can be seen with a naked eye, but the surfaces are still hot, which makes them white stars. We call them white dwarfs. And then all these stars, the white dwarfs, must be small because they radiate very little energy. Here's the diagram, the Russell-Hertzsprung diagram. So what you need to notice here is on this axis here, the horizontal axis, you have temperature in kelvins. And then if you look at the vertical axis, you have luminosity, where the luminosity of the sun is 1. So here's 1. Here the luminosity is less than that of the sun. Here the luminosity is more than that of the sun. And then our sun is here. It corresponds with 1 and a temperature of about 6,000 kelvins. Okay, so this is the main sequence. The stars that are here in the main sequence basically fuse hydrogen into helium. Now you can see that the red stars are towards the right-hand side, and they are relatively cool. And then the blue stars are towards the left, and they're quite hot. This is where the temperature is quite high. And you can see that some stars are more luminous even though their temperature is quite low. For example, your supergiants. You can see that your supergiants, for example, Betelgeuse is a red giant, which means the star is relatively cool. If you could have a star the same size, which is blue, then it would be much, much, much hotter. But the fact that this star is big means it radiates a lot of energy, and therefore its luminosity is quite high. Here you have a blue star, which is more luminous and also hot. That's why you have it on this side of the RH diagram. And then here at the bottom, you have your white dwarfs. Now you can see that these stars have high temperatures, making them white, but they don't radiate a lot of energy. Therefore, the luminosity is quite low. For example, 0.01 times the luminosity of the sun. They are about in that region. Okay, now this takes us to the discussion of the life cycle of stars. So stars, of course, do not progress through life the same way. Just like us as humans, we don't progress through life the same way. But with stars, what matters the most is the mass. So the mass, basically, the mass of the star determines the path of the star, the stages that the star will go through from birth to death. Now, for example, I think I mentioned earlier that you need a temperature of about 10 million kelvins for fusion of hydrogen to ignite so that you can have a star. Otherwise, you have what we call a protostar. So it's where the nebula doesn't have enough energy to ignite into a full star like the sun. So if you have a star which or protostar which is 0.08 times the mass of the sun. So here M SUN is basically the mass of the sun. So if the mass of this star is 0.08 times that of the sun, then the star will not reach 10 million kelvins, which is what you need for sustained fusion of hydrogen into helium. If the star is 100 times the mass of the sun, then it will undergo fusion at a furious rate and it will explode. Now you see here in brackets, I said thermal pressure is greater than gravity. These two are actually very important concepts that you need to understand. So gravity tries to bring things together. So in terms of stars, gravity wants to collapse. It wants to sort of collapse stars. Okay, it wants to press them, make them smaller, squeeze them in. But thermal pressure, which comes from the core, from the fusion of hydrogen into helium, pushes the star out, gravity pulls the star in, and then when these two are balanced, then you have a star that is sort of calm. But of course, with changes, sometimes you find that, for example, 100 times, a star which is 100 times the mass of the sun has a fusion at a furious rate, which means that the thermal pressure is more than the gravity, and that would force the star to explode because the pressure that is pushing the star out is actually more than the gravity that is trying to collapse the star. Now, massive stars therefore have shorter lives than less massive stars. Okay, our star is more of a less massive star, so the 10 billion years that it has to live is more than the amount of time that stars that are significantly bigger basically have. Okay, so for example, our star one day will run out. That is meant to be hydrogen, not oxygen. My apologies for that. Our star will eventually run out of hydrogen with time, and then it will start collapsing because it will mean that gravity is now more than the thermal pressure. Okay, however, the gravity would still cause it to heat up significantly. But what's going to happen now is it will be the hydrogen that was inside the core that is finished, but you still have hydrogen that was outside the core. Because the gravity is collapsing the star, it will make the star heat up significantly, and that will cause the hydrogen that is outside to start fusing now. The star, therefore, 5 billion years from now will grow bigger and it will eventually form a red giant. It will grow so big that it will engulf the orbits of the three inner planets that we have, your Mercury, Venus, and Earth. That's how big the star would be eventually. However, once all the hydrogen has fused, it will contract again. Okay, so it's a matter of pressure, thermal pressure versus gravity. You have more of this, you have less of this, depending on the fusion that sort of takes place. Of course, gravity depends on the mass, so it pretty much remains the same, but the thermal pressure depends on the fusions that are taking place in the star. Okay, now once the hydrogen is finished, then remember the hydrogen is fusing into helium. Now you have helium in the star. Now with enough energy, helium will also fuse. Now in this case, the helium will be fusing into carbon. Now, since it fuses into carbon, of course, it radiates some energy. So now you have an increase in temperature, which would make the star to shift from red to blue. So now the star is getting hotter. It's big, it's a giant star. Okay, now it shifts because the temperature increases into a blue star. However, once the fusion is completed, there is not enough energy for the carbon to fuse. Right now you have not enough energy because now your helium has fused into carbon, but now the carbon doesn't have enough energy in order to fuse. Therefore, because you don't have any fusion, it simply means you don't have any thermal pressure. What means this time is gravity. So now gravity collapses the star, makes the star even smaller, okay? And that leads to the formation of the white dwarf because the radiation has sort of ceased inside the star. Now, the white dwarf will eventually stop emitting light with time. This will take a very long time, okay? And eventually it will disappear, meaning it will no longer be detected by the equipment that we have here on planet Earth. Here's a diagram that basically tries to explain that. So we are in the main sequence. This line here basically represents the main sequence. These are the stars that fuse hydrogen. These are hydrogen burning stars, okay? Fusing hydrogen into helium. Now, once the hydrogen is finished, then it will move into becoming a helium burning star. And the helium burning star will form carbon, for example, and then this will take the star into a red giant phase of the star, and with increase in temperature, then it will eventually get blue, becoming a blue star. If you remember the RH diagram, where number 4 is, this is where we have our blue giant stars. And then when the carbon can no longer fuse into anything, then the gravity will collapse the star and it will move into stage 5, which is where your white dwarfs are. And here, the luminosity of the star has decreased significantly, although the mass of the star is still significantly, the mass of the star is still a lot. It's still a lot. It's like you have the density of this dwarf is significantly high because you have squeezed in all the matter, most of the matter that was there initially into a small dwarf. That's why we call them that, into a small star, okay? The only thing is that now the star doesn't have enough fuel to continue burning and eventually it disappears. Again, now this takes us to a nova and a supernova. Nova basically means new, and I think in Mozambique, every time I visit Mozambique, I learn a bit of Portuguese, and I do remember that nova has to do with new. Okay. Now, although nova means new, a nova is not a formation of a new star. It's like sort of like a resuscitation of a pre-existing star that has ran out of its own fuel, but it's not necessarily a creation of a new star. What actually happens is you have two stars that are sort of close to each other, sort of orbiting around the same point. And one of the two stars will run out of its hydrogen and go through the process of helium forming another element and so on, and eventually get to a stage where you can't have any more fusion, and that star would become a white dwarf because gravity would have collapsed it. Now, what happens is if there's two stars, one star still has hydrogen, the other star has run out of hydrogen, then the star that has run out of the hydrogen, which is the white dwarf now, will steal hydrogen from the neighboring star. And now this creates a layer of hydrogen on the surface of the white dwarf, okay? And this layer will eventually ignite in a thermonuclear explosion. Because the more you get your hydrogen, is the more you're increasing the compaction of the white dwarf, and eventually there will be enough to ignite the surface in a thermonuclear explosion. Now that explosion is seen as a nova. You can have a lot of explosions taking place, ranging from weeks to even years. Okay, here's a diagram that basically shows that. So here you can see on the top right of the screen, you have a white dwarf. It has run out of its fuel. Now you have a star here, for example, like a sun, which still has, the sun, like I mentioned earlier, still has a lot of its fuel, still has a lot of hydrogen to go. 4.5 billion years to go before it starts shifting out of the main sequence into other forms. Now, in this case, the white dwarf will be stealing, in a way, hydrogen from this star to form the layer of hydrogen on the surface of the white dwarf. Eventually, it will ignite, and this is what we see as a nova. Okay. Now, a supernova is different because it basically marks the end of a star. Now, the fate of stars that are greater than 10 times the mass of the sun is actually quite different. Now, these stars do not shrink. Now, instead, remember we talked about stars that are shrinking to become white dwarfs. These are stars that are similar to that of the sun. But if the star is 10 times, when you get to carbon, to the stage of carbon, you find that there is enough energy now. The carbon will fuse into other elements, for example, magnesium, neon. Eventually, the fusion leads to the formation of iron, and that basically brings it to the end. Now, once iron has formed, the fusion will stop. Now, when fusion stops, what you need to remember is that gravity dominates, okay? Now, the formation of iron simply means the fusion stops, and therefore the gravity will start dominating. Now, the star will collapse, and this collapsing of the star will be so quick such that it creates shock waves. Remember, shock waves will be moving in every direction, okay, from the core of the star, okay, the ion-rich star. So the shock waves will be pushing, or will cause the outer part of the star to explode, okay? Remember, the star fused into iron, and then because there was no longer fusion, gravity basically collapsed it in quick time, and that causes shock waves. Now, these shock waves will cause the outside of the star to explode, okay? Now, what remains in the super dense core after the explosion has taken place, so that explosion is what we see as a supernova. It gets so bright that it outshines the galaxies and basically stars, other stars, and everything that you basically see in space. Now, the remaining core will be super dense, very, very dense, more dense than what you had in your white dwarfs. This is many times dense, okay? It is so dense that the protons and the electrons that are found in that star will be crushed, and they would form a neutron, okay? They will be crushed into a neutron. Now, this simply means that the core of the star may survive as a neutron star, or it can even proceed into becoming a black hole. Now, black holes form when you have stars that are big, that move past the neutron star phase, okay? So you have different phases. You have stars that will end with being white dwarfs. You have stars that will eventually be neutron stars. I read somewhere that when neutron stars come back to life, they're now called zombie stars. And then you have stars that eventually proceed into becoming black holes. Okay, now here what we need to remember first is escape speed. If you remember escape speed, that is the amount of speed you need to project an object at directly upwards. Okay, so on Earth, the escape speed is 11.3 kilometers per second. So if you want to send anything out of the Earth's gravitational boundaries, then you'll have to give the object 11.3 kilometers per second, and it will be out. But it will still be within the solar system because you still have the sun. Now, if you wanted to escape the solar system, then you need to give it 620 kilometers per second, which means after 1 second, the object must have covered 620 kilometers per second. That way it will escape. It will escape the solar system, and it will be somewhere in space, not in our solar system. It will, of course, be within our galaxy, the Milky Way. Okay. Now, for a supergiant that has collapsed, the escape speed can increase to the speed of light, which means now you need an object that can move as fast as light. And as we understand it, light is the fastest thing in the universe. Okay, nothing is faster than that. Now, black holes are basically locations that can deflect light, and they can even capture it. Remember, you need an escape speed in order to escape something. Now, in a black hole, you find that not even light can escape. It doesn't have the speed of light is not enough to see it escaping. Okay. Uh, there is also one distance that sets photons in motion, which is called the photon sphere. I will show a diagram of this in the next slide. Now, what you need to understand is that a photon is a tiny particle of light. So there's a distance outside the black hole where photons can be set in orbit. And in this sphere, photons can still escape. You know, you can send a spaceship there, and then it can collect some information. It can send it back here on Earth. But then um, or like I said, the spaceship in a photon sphere can send information back here and can also escape. But we have what we call an event horizon. Now, this is a boundary where light cannot escape. Okay, it's further down from the photon sphere. So if you look at the diagram here, you can see that here's the photon sphere. Okay, so if you can get a spaceship here, you can see if it's closer to the photon sphere, you can send light in various directions. If it moves further down, you can send some light, but then some of it will be bent, okay, because of the gravity of the black hole. So the light is finding it difficult to escape. If it moves even further, then most of the light will be bent backwards, while some of it will still escape. But then once you get to the event horizon, none of the light can escape. So the diagram on the right basically shows a black hole. That dot there shows you that a black hole, its gravitational force is so strong that it can curve light. So you have light rays that are moving to the right, but those that are close are basically curved more than those that are far away. So this basically shows that the gravitational force of a black hole is so huge. Now that takes us to the discussion of galaxies. A galaxy is a huge collection of gas, dust, billions of stars, their solar systems, and so on that are held together by gravity. Now we have what we call Cepheid variable stars. Now these stars are actually quite useful. They were quite useful in measuring the distances of galaxies. For example, the nearest galaxy, the Andromeda galaxy, we are in the Milky Way galaxy, but there are other galaxies rather, some smaller than ours, some bigger. You know, in space, there's a lot of variations. You find things that are big, you find things that are small, you find things that are smaller than you find things that are bigger than you or bigger than where you are. For example, our galaxy, some galaxies are bigger than this one. Some galaxies are actually quite smaller than this one. Some stars are bigger, some stars are smaller. You know, you have all these things. You have exoplanets, some of them are bigger, some of them are smaller, some of them are the same size of our own planet. There's a lot that is happening in space. Okay. Now these variables are useful. The Cepheid variable stars were actually quite useful in measuring distances of galaxies. Why were they so important? Because the brightness of these stars can change over short periods of of time. You find that sometimes the star is brighter and sometimes it's less brighter, depending on the helium in the star. Now, by measuring the rate at which they change their luminosity, sometimes getting brighter, sometimes getting less brighter, the distances of these Cepheid stars were estimated. And they were found to be much further away than any star within our galaxy, which simply means there must have been another collection of stars somewhere. There must have been other galaxies out there. Now we need to go back now to Doppler effect in terms of sound. Now, what we understand with Doppler effect is that if you have a source of sound moving towards you, the frequency of the sound that you hear from that source is high. Because the waves are sort of compacted. But as soon as it moves past you, then the waves, the wavelength sort of increases and the frequency that you hear gets lower. Now, let's talk about that in terms of light, okay? Because we understand that the color of light can be associated with the frequency of the light. So if you have an object that is emitting light and it's also moving towards you, then you're most likely going to see a bluish light because the frequency will be high. But if it's moving away from you, then you're going to see a red color because the star or the object that's emitting light is moving away from you. Here we're talking about objects that are actually moving quite fast. So colors of stars or galaxies that are moving away from us shift to red because of Doppler effect. They're moving away from us. We get a lower frequency. Low frequency corresponds with the color red. Okay, now the degree of redshift can be measured qualitatively by focusing on the line of spectrum of hydrogen. Now, the visible spectrum of light from hydrogen basically displays these wavelengths. You have your 410 nanometers, 434 nanometers, 486, and you also have 656. Now, these corresponds to the emission of photons by electrons in excited states that are transitioning to new quantum levels. Now, if you have a greater shift in the lines of hydrogen spectrum, then you know that the galaxy or the star is receding at a very high speed. So it's moving faster away from us here on Earth. Now, using these variable stars that change their luminosity every now and then, and the stellar spectra, then distances and the redshifts of galaxies were determined. Now, our galaxy is the Milky Way. It consists of a billion of billions of stars, and we see it as a faint band of light that stretches across the sky. Sometimes if you look up in the sky, you can actually see just not necessarily the whole galaxy. It's nearly impossible to see the whole galaxy, but you'll be seeing a section of the galaxy and it would look a bit milky. And that's why the Greeks called it the Milky Circle, or the Milky Road, or Milky Way, as it was called by the Romans. So the common understanding was that there was something milky. Now, the diameter of the Milky Way, the galaxy where you are watching this video from or this presentation from, is about 100,000 light years. Okay, that's the diameter from one edge to the other. It's about 100,000 light years. And there are other galaxies, of course, that may range from about a millionth the mass of our galaxy, the Milky Way, to some 50 times more massive than our galaxies. Now, they have more mass that can also be seen with a telescope. A small portion of the invisible mass is matter that has become cold and doesn't emit light. You know, you still have matter in space that doesn't emit light anymore, and it has gotten extremely cold, which still contributes to the mass of the entire galaxy. Now we have different classifications of galaxies. We have three main classes, which are elliptical, spiral, and irregular galaxies. We are in a spiral galaxy. The Milky Way is a spiral galaxy. Now, elliptical galaxies are the most common. They are spherical with stars crowded towards the center, and most of them contain little gas or dust. Now, it makes them easy to sort of see through them. They are also mostly yellow, which means they consist mostly or mainly of older stars. Now, older cool stars are yellow, while new hot stars are usually blue. They're still hot, okay? they tend to be more blue. And then you have more elliptical stars that are, most elliptical stars are quite small, and they contain fewer than a billion stars. You do, though, have large elliptical galaxies that are about 5 times the Milky Way, but you also do have small galaxies, rather, that are about 100 times as large. Here's an elliptical galaxy on the left-hand side here. You can see the shape is elliptic, and then here's a spiral galaxy on the right-hand side. Our galaxy, like I've said earlier, is a spiral galaxy. So you could be somewhere here, but it's not even easy to spot a planet here. What you see is basically light from a collection of stars that you have in that galaxy. Now, spiral galaxies have a spheroid central bulge here, surrounded by a flat rotating disk of stars. See, these stars are rotating around the central bulge. Now, this is made up of old dimmer stars and is believed to contain a supermassive black hole. And sometimes these galaxies, the elliptical and the spiral galaxies, would come together and they would cross paths and they would eventually collide. And in such cases, the gravity will cause their shapes to be distorted, and once they're distorted, they become irregular galaxies. Now, these galaxies are normally small, faint, and difficult to detect, and they tend to contain large clouds of dust mixed with young and old stars. So the young stars will mostly be blue, and the old stars will mostly be yellow. So you have a diagram here that shows the ground view showing an irregular galaxy from a collision of two galaxies. You can see here you have a galaxy and another galaxy, they collided here, and this is what you get. So this is now an irregular shape of a galaxy. Now the blue shows the formation of new stars as the two spiral galaxies combine. You can see there's like a blue light here showing the formation of new stars. Now we have active galaxies. We talk about galaxies in terms of what's happening, the activities that are happening inside those galaxies. Now, the activity may include star formation, supernova, energy releasing processes at galactic cores. Now, regarding stars formation, if you look at our Milky Way, it is relatively calm. It produces like a single star each year on average from a nebula. Okay, then you have star-based galaxies that are very active. They can produce or that galaxy can produce about 100 new stars in a year. So it's quite busy in that galaxy. Now this may be due to a violent disturbance. It may be collisions between two galaxies. Once the disturbance ends, a starburst tends to die as well. Now, I have many elliptical galaxies that are believed to be former starburst galaxies rather, because of their low abundance and interstellar dust and gases. And of course, other galaxies are active because of their galactic cores, which host a black hole more massive than billions of suns. You can take billions of our suns and put them together, you'd find that the black hole is still more massive than them. So the Milky Way also has a black hole in the center, which is the source of its activity, although it remains basically calm. And then we have clusters and superclusters. This is basically the classifications of galaxies. Galaxies tend to cluster into distinguishable groups. You have local groups of galaxies that also get influenced by the gravity of neighboring galactic clusters. Okay, now this results in a supercluster, which is a cluster of galactic clusters. You get galaxies that sort of cluster together, and then you also get a cluster of clusters, which is now a supercluster. Now, local clusters are also tied to other superclusters. They appear as if they reside on a surface of form, form when you wash dishes or clothes, and you get that form, and it appears as if these clusters are basically located there. Now, zooming out shows that the superclusters will extend to the edges of the observable universe. So galaxies, like I mentioned earlier at the beginning, you have your universe, and within your universe, you find these galaxies that can be clusters or superclusters, but within the galaxies, you find stars. Now, these stars can have their own planets, okay, making up a solar system and asteroids. But a planet can also be orbited by a body of mass, a body of mass rather, and which we call the moon. And you find that on a certain planet, for example, ours, we have the atmosphere, we have uh, rocks, we have minerals, we have a whole lot of things. We even have life. So what you need to understand is how huge the universe is, and the fact that it ranges from the smallest of particles to bigger objects, to the edge of the universe itself. So the range of things that you find within the universe is actually enormous. And you think about the temperature as well, moving from the absolute zero, which is the lowest possible temperature for anything, and you can move all the way up to hotter stars that are blue in color. So there's a lot that is happening in the universe. And like I mentioned earlier, you find that it is so difficult for our brains to sort of comprehend exactly what is happening. Why is space expanding at such a high rate? And why do we measure, or why are these objects, some of them so far, for example, stars that we tend to measure them in light years and so on. So I do believe that this presentation will help you sort of understand some of the concepts that may have been complicated if you were reading them by yourself. Thank you very much. That brings me to the end of the presentation.